normality is a restriction you can impose on states on a von Neumann algebra that's so clearly imposed in ordinary quantum mechanics that imposition is unremarked. So the topic of this talk is, should we impose it? And the plan is, first I'll talk about the nature of the restriction and the conditions under which it makes sense. Next I'll parade some temptations to resist imposing the restriction in the form of states that aren't normal that might do us some good. And then I'll consider, I should make this clear at the outset, I'm not going to lobby for a particular answer to the question, should we be normal or not, so much as catalog the kind of considerations different lobbyists might bring to bear, with a view towards appreciating the variety and scope of this consideration. But I'm going to consider 4 different reasons one might give for imposing the requirement of normality. 2 of them, maybe more than 2 more, and then they'll be answered. So, a state omega on a von Neumann algebra M is a map from n to the complex numbers, where you think of the image of the map for the self-adjoint elements and expectation values. That satisfies certain sanity conditions. It's linear, it takes positive operators, non-negative expectation values. It's normed, that is, it takes the identity operator, which you might think corresponds to a tautology to the value 1. So those are all pretty straightforward and saying. A state out of a von Neumann algebra is normal if it satisfies this additional condition, which is more or less a countable additivity condition. It's normal if for any countable set of pairwise orthogonal projection operators in the algebra, the state maps the sum of those projection operators to the same number as you get by summing what it maps the operators to. The normal states are countably additive. You're probably familiar with them as the states described by Casey's here. That's the operators of the one space dimension 3 or 4. Contemplating the nature and virtue of normality. One question you might ask looking at this condition is, what's that? That's an infinite sum. What's that? How do we make sense of that? Infinite sum. Raising that question gives me an excuse to reflect on the prescience of Plato, who in the Sophist remarked, all discourse owes its existence to the interweaving of forms. The Greek word for interweaving there is symplicate, the same root as the root of the word symplectic, so if you read it in the right mood. All discourse owes its existence to symplectic forms. Here's a recipe for quantum physics discourse, not the only one. You start by finding operators all hands are going to agree are physically significant operators. I don't know, it's doing quantum physics. These might be operators that satisfy canonical commutation relations, canonical anti-commutation relations, the physical relations between observables that are constitutive of the kind of physics we do. But you don't want to stop there. You want to make some discourse by doing some more interweaving of forms. So one thing you might do with this seed set of operators is start forming products and linear combinations. For instance, building Hamiltonian observable positions. You might not even want to stop there. You might say, having built a Hamiltonian observable, to exponentiate it to obtain a unitary operator. And that might entail understanding that unitary operator in terms of a limit of a sequence of operators that we already obtained in terms of linear combinations of products. So, in your project of interweaving forms in the service of framing a physical theory, a question's going to come up. Which sequences of operators I'm already committed to as being physically probative have limits of sequences converge. What you're doing, you start taking linear combinations and adding products and adding limit points, is building an algebra with the canonical observables as generators. And you feel the need to add limit points if you confront the question, which sequences converge, which sequences have limits. And Hilbert spaces make available, that's not too faint to see, a number of different criteria for when sequences converge. Sequences have limits. One criterion, this is probably going to be familiar with most of you, one criterion is afforded by the norm operator topology, which I've written down. I'm not going to go through the details, but I'll tell you what the details are. One criterion of convergence is afforded by the norm operator topology, which says operators converge when these conditions are satisfied. There's a mare's nest of other criteria of convergence. One is that afforded by the weak operator topology, which is using a whole set of vectors to define one norm, uses each pair of vectors to define the semi-norm and convergence in terms of the behavior of that set. So there's these different criteria of convergence. The point is some criteria of convergence are more permissive than others. Some criteria of convergence make it easier for sequences to converge than others. Again, I'm just going to say what's important. So a kind of the standard example of a sequence that converges in the weak operator topology, but not the norm operator topology, is a sequence of partial sums over a countable, complete orthonormal set of projection operators. That sequence of partial sums doesn't converge in norm. It's a very faint thing I've added. Here's the argument that it doesn't. But that sequence does converge in the weak operator topology to the identity operator, the space for which the projection operators are. So we're interweaving forms, we're building an algebra, we want to do physics. We realize we want to add limit points. We face a decision, how are we going to define limit points? What criteria do we use to define limit points? If we use this stringent norm topology, according to which the complete orthonormal set of projection operators, they're partial sums, it's countable, doesn't converge, we get a C-star algebra. C-star algebra is an algebra more closed. If we use the more permissive criteria of convergence afforded by the weak operator topology, we get the kind of things we've been talking about. I've been talking about the kinds of things for which normality is a criterion of acceptability on state-space sets of von Neumann algebra. So remember the question that started this digression. The statement of the requirement of countable additivity included this thing, this countable sum of orthogonal projection operators. How are we going to understand that? We're going to understand that in terms of the von Neumann algebra as strong limit, the sequence of partial sums. There's going to be no impediment to imposing the requirement of countable additivity because the closure properties of the von Neumann algebra ensure that if the projection operators you're summing over are in the algebra, so too will be the thing that's their sum. I just assured you that as long as we're talking about von Neumann algebras, this thing that appeared in the criterion of countable additivity, the definitive of normality, makes sense, but not more explicitly if understood this way. This area is normal. I'm not going to try to read it in words. And I hope this makes plausible. I'm going to show it. I'm just going to claim it as a fact. That an equivalent way of characterizing normal states is states that are nice with respect to the topology used to complete the von Neumann algebra. The particular topology, the ultra-weak one, define density operators, one of the more permissive ones, but the requirement of countable additivity that's familiar is equivalent to maybe this less familiar requirement. A state of A is normal if it's ultra-weakly continuous in the sense that again, a sequence of operators of I that converges ultra-weakly to some operator A, then the normal state will be such that the values that assign the A sub I converge to the just an equivalent characterization of normality. And the point of exposing this equivalent characterization of normality is it'll give us a different way of approaching the question why is normal, other than by turning our fists and saying countable additivity is good. Approaching the question why be normal by way of noticing ways continuity informs our sense of what makes physical systems physical. That was a section of the talk telling you what's normal. Now I'm going to chronicle things that might strike you as temptations to abjure normality, temptations to make use of states that aren't normal, to make use of them thanks to their possession of representational capacities you might not have. So here's one example. It's the dreaded infinite chain of electrons. So we're ready to do quantum mechanics, we're infinite chain of spin one-half systems. We're going to build up on Neumann algebra as follows. We're going to assign a trio of Pauli spins to each system satisfying Pauli relations, and we're going to have these spins acting on a symmetrical Hilbert space spanned by the basis vector I've drawn up here. It's an eigenvector of spin z for each site pointing up. And a collection of other basis vectors differing from this basis vector in prime dimensions. And this all works. Represent the canonical and commutation relations. So this is our von Neumann algebra. And now I'm going to exhibit a state that you might think is a physically relevant state, a very nice state, a state we shouldn't shun. That's not a normal state on this von Neumann algebra. There's probably more direct and elegant exhibitions, but I'm going to do it this way. In this von Neumann algebra, I'm calling n plus interweave some forms to define an observable magnitude that is an average over n sites of their spins in the z direction. Because we're going to be interested in this. For instance, we can start drawing phase diagrams of a ferromagnet. Notice how we love phase diagrams of totally different systems. So we define the average spin that way. And it might be plausible if you think about the basis vectors in the space, and how they're always going to have infinitely more spins z ups than spins z downs, that in the limit as n goes to infinity, this average of the z component of the spin turns out to be the identity operator. It takes value 1, expectation value 1 in every state in the space. And in fact, this spin I've defined here as n goes to infinity converges ultra-weakly to the identity operator. Remember, ultra-weak continuity is the defining feature of all states. So in order to, one way to show that a state is not normal was to show that, even though n converges to the identity as n goes to infinity, the expectation values it assigns and n don't converge to 1. So here's such a state. It's just the state that's the flipped over version of the seed state for my Hilbert space, the state that assigns every spin in the lattice spins z. So it acts on the spin z guys in the algebra and acts on the minus 1. It's going to follow that for each m, the average over n in the spin z in this state defines is minus 1. So the limit as n goes to infinity is minus 1. However, because it's a state, I'm calling the state omega minus obvious reasons. Because it's a state, the state's got to do this. It's going to assign the identity operator for 1. So even though the average spin converges to the identity operator as n goes to infinity, the expectation values the state omega minus assigns the average spin don't converge to the expectation value 1 as n goes to infinity. The state's not ultimately continuous, therefore this state's not 1. So you might want to invoke normal states because you think there's physical states of affairs that you can't adequately represent using only states that are normal with respect to an algebra. Here's another example. These are my prima facie examples. Might not be persuaded. So the algebra, the von Neumann algebra we're going to talk about here is an abelian one, pairwise. We're going to take it to act on the Hilbert space of square interval complex value functions of the unit interval. The elements of the algebra are going to correspond to measurable functions of the unit interval, and they're going to act on the Hilbert space as square interval functions just by multiplication. So this blue line with the value 1 across the unit interval, that's the identity operator. Take that square interval function and multiply it at each point by that function in an element of Hilbert space. There's going to be lots of functions in this algebra, this von Neumann algebra. I'm calling DQ. Let's pay attention to what turn out to be the projection operators in this von Neumann algebra. The projection operators are just characteristic functions for subsets delta. Characteristic function for the subset delta is going to be a function that x, if x is an element of delta, takes the value 1, takes the value 0 outside. projection operator. I'm working my way towards exhibiting a state on this algebra DQ of functions on the unit interval. That's not. So we're going to need to take on board some facts about operators. There's going to be facts about the projection operators, the characteristic functions. One fact, you can persuade yourself of this by thinking about how the different things I'm talking about act on arbitrary square interval functions. One fact is if the subsets of the unit interval delta and gamma differ by a set of measure 0, then the projection operators, the characteristic functions associated with them, are the same. So these characteristic functions are characteristic functions for subsets of the unit interval up to measure the different up to measure 0. Now, a non-normal state on this algebra DQ. Here I'm following. I'll stop. Here I'm following very, very nice article by Hans Holgersen. Continuous physical quantities. So I'm going to call the state the non-normal state. Try to mention it's not normal and try to make it seem like an interesting state anyway. Omega lambda. I'm going to think of omega lambda as a state that converges to a point lambda in the unit interval. And to make my life easy, I just decided the point lambda, the real number lambda, is 1/2. I'm going to tell you some things about how this state omega lambda acts on the projection operators. I'm going to tell you these things by way of introducing a family of subsets of the unit interval delta sub I. Delta sub 1 is the whole unit interval. Delta sub 2 is half of the unit interval centered on 1/2. Delta sub 3 is a quarter of the unit interval centered on 1/2. So pictures of these values converging to the point lambda. And here I'm telling you how the state omega lambda acts on characteristic functions. The characteristic function for set gamma is mapped to 1 by omega lambda if and only if one of the deltas, one of the intervals shrinking to the point 1/2 in this family is contained. It's intuitively supposed to capture the idea that one thing omega lambda is sure about is that you're at lambda. Omega lambda converges to lambda, starting down the road toward a state of the system located with probability 1 at lambda. I have many reasons for thinking there are such states. Now this state omega lambda isn't normal. Here's an argument that it's not normal. In terms of the projection operators for the shrinking families, let me introduce a complete orthonormal set of projection operators I'm calling EI, where E sub I is going to be the difference between the ith member of the family and the I plus first member of the family. So E1 is going to be the projection operator for the first quarter and the last quarter. So these things, the sort of differences between subsequent elements, the characteristic functions of this family delta. They're going to be a countable set. They're going to sum to the identity. They're going to be pairwise orthogonal. And if you think about it, they're going to be such that omega lambda assigns each and every one of them to 0. Omega assigns each and every one of them to 0 because in each case, EI is going to be orthogonal to some projection operators and characteristic function that, according to our rule for omega lambda, is mapped to 1. So that means omega lambda has to assign each E sub I at 0. So here we have a situation where the E sub I, they sum to the identity operator. Omega lambda assigns each E sub I value 0. Omega lambda assigns the identity operator value 1. Omega lambda is violating the requirement of countable additivity. Omega lambda is not normal. It's an exact position eigenstate. That's one way to think of it. You can think of the projection operators I'm talking about as the spectral resolution position operator, and omega lambda is the thing that describes a system located at point lambda. So Another reason you might be tempted to flout normality is you want to talk about exact position. Here's a different kind of reason to flout normality. Maybe I'll talk about quantum field theory. So there's an interesting difference between the two examples of states that are normal. In the first example, the state omega minus on the dynamic algebra m plus. There are pure normal states on dynamic algebra m plus. All the states in the Hilbert space H plus, all the vectors in the Hilbert space H plus are pure normal states on m plus. By contrast, the abelian von Neumann algebra DQ, the guides projection operators on the spectral resolution of the positions. This guy has no normal states for pure. None of the projection operators are minimal. That's the technical reason. But it's an algebra that has this weird feature that none of its pure states. Algebra with that weird feature that none of their pure states are normal are endemic in quantum field theory and in the quantum thermodynamic and quantum statistical mechanics. So here's some ways to get algebras with this weird feature that none of their pure states are. You put the free Klein-Gordon field on Minkowski spacetime, you subject it to standard axioms. That's supposed to be a diamond. That doesn't say, you consider a region as non-empty space-like complement. And it's going to follow from the axioms that the algebra, one of the algebra observables associated with region, is an algebra that has no pure normal states in this general system. And the thermodynamic limit of quantum statistical mechanics is going to turn out for a wide variety of systems. The states corresponding to equilibrium states at temperatures other than 0 are going to generate von Neumann algebra that emit no pure normal states. What's this got to do with, or how does this underwrite motivation to flout now? Well, there are in the offing a lot of interpretations of ordinary QM, ordinary quantum mechanics, that proceed by way, whether they think there's measurement collapse or not, they proceed by way of using pure states to encode the facts about quantum systems. The sort of most blatant version of this is the ignorance interpretation of mixtures. Mixture, especially a statistical one, you think there must be some pure state in the system. But most no-collapse interpretations work the same way. You think, notwithstanding being described, if you're, say, a Modo interpreter, notwithstanding being described by a superposition after a measurement, Schrödinger's cat has determinate values for Biolow's limits. Develop your modal interpretation in such a way that you use a pure state to encode what those value intervals are. Some people call these the value states, the things that encode the truth about quantum systems. Maybe they're distinct from the dynamical entities that Schrödinger involves. But if you use pure states to encode the possible conditions of quantum systems, there's certain nice consequences. For instance, one of the payoffs of using pure states to encode the condition quantum systems are known in is you can generate determinate value assignment to abelian Boolean algebras of observables that are maximal. So if you're committed to use pure states as value state encoders, you're saying that in principle you can say about a quantum system. So there's existing interpretive predilections that say in order to make sense of the conditions quantum systems are in, we don't necessarily need collapses to pure states. We don't necessarily need the dynamical states of systems to be pure states. But we need pure states to keep track of what the truths are. Now, if you want to extend these interpretive predilections to the setting of quantum field theory or quantum statistical mechanics, thermodynamic limit of quantum statistical mechanics, you're going to run into the impediment that in many, many algebras of observables of interest, there are no pure normal states. So in the face of that impediment, you're going to hold tight to the commitment to use pure states to code the condition the system really in. You're going to need to use states that are normal. much more roundabout temptation to flout normality. Temptation. There's temptations to flout normality. Next section of the talk. So what is normality? How we know. Here are some cases where we might want to give up on normality, not going to consider some reasons to insist on what might be. A set of 4 reasons that I'm going to talk about, 2 of them more than I talk about another 2. So one is just amounts of help. I think there's probably interesting ways to develop this kind of case for insisting on normality. I don't know what they are. I don't know how to get traction in a case like this. Just countable additivity is just decent. And there's just something obscene about states that violate countable additivity. There's just something off about I don't know how I feel about that or how to intelligently pursue a debate like that. But I will make the observation that you can read while I'm drinking my water, that countable additivity is a virtue states exhibit in assigning probabilities. If you're of the camp that thinks the temptation to recognize states that aren't normal is that you need, in certain circumstances, states that aren't normal to do the job of value encoding pure states, then the non-normal states you're countenancing aren't in the business of assigning probabilities. They're in the business of receiving probabilities. They're in the business of keeping tabs on the value states over which some Schrödinger-Ribal state or whatever is defining a probability distribution. One thing you might think is that if you're out to non-normal states, if you want pure states as value state encoders, maybe you don't need to worry too much about the original countable additivity because you're not using these things to assign probabilities. You're just using them to characterize the conditions that you see. So this is one of the reasons to be normal. Here's another consideration I can imagine. It derives from considering quantum state preparation. What's a quantum state preparation? Understand it this way. A quantum state preparation is an interaction with a quantum system that has the result that subsequent interactions are in the scope of quantum probability assignments. It's something we can do to a quantum system that enables us to use the quantum statistical algorithm to make empirical predictions. Prepare a quantum state. There's a physicist in a lab, he's got a measuring device. He wants to get quantum systems into a condition from which he can extract probabilities for the measurements that he wants to prepare quantum systems. And here's a kind of, I think, uncontroversial and non-weird story about what makes preparation positive. Kind of standard story. Preparation is pre-measurement. So the story is something like, when the system enters the lab, we don't know anything about it, except on the story, and it's in some normal state. But before we subject it to our end measuring device, we subject it to a preparation interaction. We run it through a Stern-Gerlach magnet. This field's inhomogeneous in this direction. If it emerges from that pre-measurement interaction in the up trajectory, obtain the outcome of the pre-measurement spin up, then we're authorized to do something like Luder's conditionalize on the outcome. Whatever state it was in before the pre-measurement interaction, subsequent interactions are going to be in the scope of the condition that we got the outcome associated with the direction operator and all. So Luder's conditionalize on the outcome we got. And then it's a happy fact that when we Luder's conditionalize on the projection operator such that the outcome spins the up, no matter what the normal state of the system was before the preparation interaction, it's going to be the state encoded by that very projection operator after the preparation interaction. Don't forget about the job we did there. So that's our story about preparation. We managed to prepare things because we can apply Luder's conditionalization. And there's states such that, oh, maybe I can Okay, I'm going to call a projection operator in a binomial algebra. I'm going to call it E5. I'm going to call it a witness for, that should be a state omega on the binomial algebra. Just in case for any normal state omega on that binomial algebra that assigns, in a way to give you a more precise state, whose witness I'm looking for, expectation value different from 0. When you Luther's conditionalize an arbitrary state on the witness, you get the state of which is the witness. The projection operator onto the eigenvalue spin z is a witness for the eigenvalue spin z, because no matter what normal state you Luther's conditionalize on that projection operator, that outcome, you get in place. So the story of preparation is the story of Luther's conditionalization and the presence and the binomial algebra we've been talking about for these things I'm calling witnesses. My physicist is going to play to summarize how to prepare state phi on a binomial algebra, and she measures the predicate operator that's a witness for phi. If she obtains the outcome 1, she's allowed to Luther's conditionalize, and the result, no matter what this normal state of the system was before measurement. Template for kind of coverage. Now, why be normal? Why be normal is recognizing non-normal states as well as normal states throws a wrench in the works of this strategy for kind of coverage. So here, some facts. If omega, say omega, I don't know enough is normal, and we're considering some projection operator on that binomial algebra, then omega conditionalized, Luther's conditionalized on that projection operator is going to be normal too. Because in tangents, if the state psi on a binomial algebra isn't normal, and you Luther's conditionalize on some element of the binomial algebra, the result isn't going to be normal. This is because normal states form what's called a Foley, or not Foley, it's a Foley's number. Something that has Luther's visualization as a case. So what this means is, if we think there's both normal and non-normal states that are possible states of our system, we can adapt this account of preparation to make sense of preparation of any state. There's nothing that's going to be a witness for any state if there's both normal and non-normal states. There's nothing if you have normal states that will enable you to compare non-normal states and vice versa. So the equation formula under Luther's conditionalization. And then a sort of further complication and keeping track of this motivation of deriving from the ubiquity and quantum field theory of von Neumann algebras that admit no pure normal states. The only normal states that have witnesses at all are pure. So the kind of account of the preparation I was just sketching just can't be adapted to account for the preparation of states on von Neumann algebras that don't admit pure normal states. Can only use it for features of pure normal states. Another reason to be normal sometimes enables for those von Neumann algebras that have witnesses for states an account of the state preparation. Here's a brief reason. But let's this is written up there. Let me say it. The impediments to telling credible stories about state preparation of non-normal states might reinforce one of the lessons of the first concern about normality. Normal states aren't countably additive. Insofar as it isn't easy to see how to tell a story about how to compare states. There's normal states as well, and non-normal states as dynamic possibilities. The lesson is non-normal states are hard to make sense of as sort of predictive instrumentalities, things we compare, conditions of things before we compare things. But that doesn't impugn the capacity of non-normal states to play this value state encoding role. That's the motivation for cognitive non-normality in the case of So the next two considerations I'm going to go through are meant to impugn the capacity of normal states to play the role of fact encoders. You can track what's true. Sorry. non-normal states play a role in that. Play a role in keeping track of what's true. So, why be normal? For the sake of what I'll call affability. In the case of these von Neumann algebras that admit no pure normal states, we know that they admit pure states. But the way we know they admit pure states isn't that we build these pure states, isn't that we construct these pure states, isn't that we say for each projection operator and a maximal abelian sub-algebra how these pure states act on that projection operator. We know that there's pure states on these weird non-linear algebras by a non-constructive argument. There's something called the ultra-filter extension theorem, and if you show the ultra-filter extension theorem, that story I told you about how omega lambda acts on characteristic functions, the ultra-filter extension theorem will tell you that the omega lambda I described can be extended to a pure state. So that puts us in the pickle because the non-normal pure states on these weird algebras that have no normal pure states, because our handle on them is kind of non-constructive. They're not forthcoming anyway. So on this story, the reason we're resorting to non-normal states is to tell us what the world is like. But you can prove upsetting facts like the one Hans proved that that pure state omega lambda I introduced, that wasn't just one pure state. There's countably many distinct pure states on the G that all converge. So the things I do know about the abnormal pure states I'm invoking as my value states don't fix all the facts I think are facts to be had about the system I care about. You might be disappointed by that, especially when you contrast the reticence of these non-constructible, pure, non-normal states with nice pure states in quantum statistical mechanics that tell you for anything you think is an observable what it's not. It tells you know what value states being encoded by this pure state. In the case of omega lambda. Let's see, Rob Clifton's 2000 paper where describes a project of interpretive quantum field theory that gives up on maximality, gives up on fitting states, value states to tell you everything in principle to be said for the sake of affability, for the sake of being true. Why be normal? Well, it's not clear normal states are any more affable in these cases, but the other violence to norms in practice done by resorting to non-normal states isn't justified by the explicitness of non-normal pure states. Here's I think the most interesting reason to be normal. It's got to do with instantiation and necessity. So back to the idea that the business of physics is the business of intermediate forms. Notice that in physics there's lots of important relations between observable magnitudes, which relations involve, presuppose, rely on the existence of limits, rely on countability features. So here are some ways, some relations in physics and important relations in physics that rely on the existence of limits as an countability. So medieval time interpretation of Aristotle's physics. Aristotle always starts stuff up by telling you what he's going to talk about, what he's not going to talk about. In physics, he's going to talk about natural things. What are natural things? Are the things of natures? Natures, the principles of change and stability. The obvious difference between natural things, the things he's interested in physical things, and things that are not natural, is that each of the natural ones contains within itself a source of change and stability. Let's suppose he uses a Hamiltonian. One way there's an interweaving of magnitudes in physics that involves limits is you've got some ferromagnet. You're interested in the Hamiltonian for the whole ferromagnet. It's a thermodynamic limit kind of thing that occupies an infinite volume. You might build it as follows. You might start by considering a finite region of the ferromagnet, describe the Hamiltonian and finite region, then take the limit as the volume considering those two. So the total Hamiltonian for the system, the principle of change that renders it something with the nature of something physical, its existence depends on the existence of K2. There's interweaving of magnitudes involving limits. There's their definition. Same sort of example. I want to introduce sort of global polarization. I think it's cool. Global polarization, the definition of it in terms of other magnitudes, the definition mediated by the existence of a limit. There's what I'll call axiomatic interweaving of magnitudes. So the spectrum condition and axiomatic approaches to quantum field theory on Minkowski space-time says something like unitary groups of limited space-time translations. These unitary groups are continuous. Thanks to Stone's theory, we know they have infinitesimal generators. The spectrum condition says something about the spectrum, where the magnetize of infinitesimal generators. Spectrum condition, the axiomatic approaches of quantum field theory presupposes having a continuity of bounds in each of the operators. Anomic interweaving of magnitudes. Here's one way to express Schrodinger's law. The family of time evolution operators. It's a continuous family. It's infinitesimal generators. So the continuity family and the definition of Hamiltonian is kind of both. And the expression of these laws, this law of physics presupposes relation to continuity. So, question. Given that sometimes when we do physics, we interweave physical magnitudes in ways that presuppose or involve the taking of limits or positive of continuity, what is it for a state to instantiate these kind of all-like relationships? And here's a simple-minded answer that's probably just for that reason suspicious. When there's a law-like relationship that involves a limit, what it is for a state to instantiate it is to be such that under the action of the state, the action of convergence is mirrored, the limiting relation is mirrored in the action of the state. So Schrodinger's law is instantiated by a state if the image under the state of the family of unitary operators is because that's how the law says that action. So yet another reason to be normal. Why be normal? Non-normal states can fail to instantiate law of the foregoing states. So, or if you've seen that this state, omega minus on the spin chain, fails to instantiate the sort of conceptual relationship defining the global polarization as a limit of finite and average within the sense. And even worse, you could imagine states on the infinite spin chain, where it's not just that the global magnetization gets mapped to something, a number different from the limit of what the finite and magnetization get mapped to. There's states for which the limit doesn't exist at all. Because global magnetization isn't just overhanging, it's undefined. Particularly setting if you want global magnetization to be involved in interesting laws that are instantiated by the states. Sometimes, insofar as these infinite volume averages, like in mean field models, are part of the Hamiltonian, this kind of breakdown of limiting relationships that are possible for non-normal states entails a breakdown of the kind of existence of the Hamiltonian. It's called instantiate physics. Here's an example. Back in terms of the state omega lambda that converges. Omega of a non-normal state that frustrates and fails to be an instance of Schrodinger's law. Understood. What I recommend. So we're thinking of an evolution operator which just translates things. It translates them farther along from the weight. Schrodinger's law says evolution operators form a continuous family of Hamiltonians and self-adjoint generators. The state omega lambda I talked about before fails to instantiate this law. Wow, here's a quick and dirty argument. If you translate the state omega lambda by t by the evolution operator, you just get a state, I should say, and now we're not living on the way. You get the state omega like lambda translated by t. The way these states are defined, if t is different from 0, omega lambda plus t are going to be orthogonal. And what that means is the image of the unitary operator u of t under omega lambda is going to have a discontinuous jump at t equals 0, 0 to t. So under the actions of the state, these things are going to come into use. I'm claiming that if what it takes to be an instance of Schrödinger's laws to be such that the sorts of continuities presupposed by Schrödinger's law are respected by the expectation values you decide, this thing's out of instance. So, I think these kind of considerations I've been talking about to suggest that you can figure out your von Neumann algebra is, then maybe there's pretty good reasons to restrict attention to normal states, reasons having to do with dynamics and state preparation. Wanting the states you take to be physical, to be instances of the laws, other conceptual interrelations you take to be important. So supposing we have good reasons to focus in on von Neumann algebra, these seem like okay reasons to demand normality. But then the question becomes, do we have the reason to focus in on a von Neumann algebra? I think the answer is it depends. So, ironically, an argument of the sort I just gave for restricting physically admissible states to normal ones because the relations we care about between observables are well behaved under that restriction. I first encountered it in a paper by Siegel from the 50s, where he used it to argue for the opposite conclusion. This is an argument that argue for the opposite conclusion. The reason to resist taking weak limits as significant is if you have a really broad set of states, kinds of constitutive patterns of definition that obtain between observables are disappointed in some other states that you take observables that are weak limits of other observables. So simply noticing that there's nice ways the set of states you entertain, the set of magnitudes you entertain, cooperate with each other. Or instead of the question, which magnitudes you entertain, which states you entertain. So we can't decide which states are physical in isolation, considering what law-like relationships we care about, what magnitudes those relationships invoke. And I would also be more radical and say decisions about what law-like relationships we care about, what magnitudes those relationships invoke, we're probably going to make them in different ways under different applications of theory. We're trying to model different phenomena. If we're thinking of a theory as something we're building other theories from. So here are some examples. Schrödinger evolution, insistence that there's this particular recipe for generating a unitary family of unitary operators that are called evolution operators. It seems pretty good, but in quantum field theory and curved space-time, there's dynamical maps that have a claim to be dynamical as a collection of observables that aren't unitarily implemented. We want to make sense of the dynamicism of those maps that you never are unitary. Likewise, there's states in Minkowski space-time that don't have all the nice symmetry properties that I'd otherwise expect, but nevertheless have physical application. David talks about some of these in his GPS paper. Exactly, more transparency, I'll shut up. Illustrations of the way different things we might do with a theory might pull us in different directions so far as ruling about what observables we care about, what sets of relations between those observables might do law like. There's, what do you want to call it? The condition of state has to satisfy to assign the stress energy interval expectation value, and so for instance, support the project is of classical quantum gravity and some deliberations stress energy interval and an expectation value. Is a condition violated by a state some people think makes the most sense of what the exterior of a black hole looks like. And making sense of what the exterior of a black hole looks like is another project in the service of developing quantum gravity. So even sharing the cognitive aim of developing quantum gravity, different physicists might rule different ways using all those states. So my conclusion is the nature and desirability of normality.
I know that in that context, I think you guys argued in my paper that the one natural condition that you could impose that the states are high, moderate, quantum free isn't closed under depending on the condition. And so I'm wondering if there are other cases where that same sort of attempt to restrict to a subset of states which are normal will run into problems with closure under depending on the condition.
The example with the nocturnal doubling of space-time, like the way I know about. So the set of considerations for what motivates restrictions I've talked about include the consideration that we want there to be physical states guided with dynamics. In some cases, for instance, in fluid models, when the condition, so the condition that states dynamics distinguishes invidiously between different possible states, but distinguishes invidiously in the sense that for some states, weak operator topology of the Hilbert space, with respect to which they're normal states, the infinite volume limit is well defined and defines unitarity. So there's the drift of the sense of dynamical evolution that under which the set of normal states is enclosed is in general. There's also considerations where insisting that there be dynamics, you want to be dynamics that keep you flowing. Identifying physical outcome.
This is really a question for clarification, I think. Going back to the argument about state preparation, in the straightforward case, when there are normal states available to interpret in this way, in the way it involves linguistic conditionalization and all that, is the thought that the fact that we don't seem to go wrong by applying that kind of interpretation of what state preparation involves, is that kind of an inductive argument on past not going wrong with that kind of way of going? Like, could we expect, I don't know, could we expect that we would go wrong with linguistic conditionalization or something like that if we, I don't know, would there be some sort of consequences that we would have noticed if we were misdescribing the state preparation process? Or if there really wasn't, or if it really wasn't non-normal state?
So the question is, supposing there's like electrons flying around in non-normal states, would preparation work as well as it seems to have? So preparation pegged to the account I just gave of it, maybe it wouldn't. But there's still this kind of retreat position where what I'm doing with the non-normal states isn't assigning to one system a dynamical state, but using the non-normal state to keep track of intrusive on a quantum system and what's problematic dynamical state.
So you would expect that to be
I'm not yet.
And more or less the same kind of question, but sort of in general in all these examples. I mean, so it's sort of surprising that the choice sort of seems to come down to like our interests, and sort of sounds like it's anthropocentric or something. We get to sort of choose what we want to do here, whereas whether things can actually be in these states or not seems like it doesn't really care about us. It's about the systems. So, can you just, I mean, there were quite a lot of examples, I guess. I mean, are they all of the kind, like I think you were just suggesting there, where you might think it's pragmatic because it's really just a conventional choice? Or are they all like that, or some like that? And then, are there some where it clearly makes a physical difference what happens?
Maybe I'm just not, so the examples are various. The last bit about it's up to us preface that by saying my tendentious contention is that.
But that's more an invitation, isn't it?
Right.
Pick it up.
So taking up the invitation, I'm suggesting that you're describing as physical reasons. What are the reasons there's this phenomenon that we need the state restriction to explain? There's this extension of the theory, we need the state restriction underwrote. There's this model, we need this state restriction to support. And I believe that a symptom of that set of things not picking out a collection of states that are just physical in a sense that severs an physicality from our interests and so on is, I think for theories like this, those sort of considerations don't always pull the same way. So even understanding, you might object to this loss of physical, but even understanding what's physical as states of a quantum field on curved space-time that will help us prosecute the project of developing quantum gravity. There's ways to interpret physical so that that state isn't physical because it frustrates the assigned expectation of the tensor, and that state is physical because it helps make sense of the black hole. So the accolade of physical you want to use.
Well, the first place I was just thinking, things we can measure, if they come out differently. So it seemed like a kind of boring thing. If there were normal states, measurements would just come out differently. So are any of the cases like that, or they see the things we take as being unproblematic and measurable that sort of turn out to have the same observable values in both cases?
So the ferromagnet, if you think there's ferromagnets that, so the question whether there's normal states or not has to be indexed to specifying the von Neumann algebra, not there's no normal states. So if the von Neumann algebra is the algebra generated by spin up all the way across, then an argument you can give that there's not normal states is sometimes there's ferromagnets that suck my glasses that way, so driving them that way. So that seems like a straightforward matter that we can measure. But insofar as it's a straightforward matter of measure, I'm going to claim that regarding it as significant is conditioned by the interest in explaining ferromagnetism and the calls about which states are physical, predicated on the interest in explaining ferromagnetism, depend on particular Hamiltonians we construct for the ferromagnet. So particular Hamiltonians we construct for the ferromagnet overwrite this Aristotelian sorting of states into physical and not according to whether or not they have well-defined limits.
So would you go along with it? I mean, so in cases like that, what about if I said, so yeah, really this system has sort of non-normal states, but of course there are cases where I'm just not interested in every physical property of the system, and then it makes that though. So then I'll just ignore the non-normal states, because they're not relevant for what I'm working on. So is that what you're saying? So really there's non-normal states, say in that case, but I just sort of ignore them?
So
or is there some kind of...
I'm not trying, so I don't think there's a uniform answer.
Sure.
Okay, so I think if you want to exhibit the phase structure of a ferromagnet and you want to regard that as something nomic and is an instance of a nomic pattern that reiterates across the physical world, then you better take your physical states to be states that sustain the definition of a global polarization. And that commitment to the law-likeness of entanglement of the global polarization in patterns that are instantiated by all physical states, legislates the restricted physical states to states for which global polarization can be found. But I can't, because I'm talking about ferromagnet, think of cases where different questions you might ask about a ferromagnet and legislate for taking a different set of states to be visible. But I think there's examples where about the same system, different questions arise such that the kind of law-like relations you want to invoke to answer those questions in order to be understood as law-like relations require different sets of states. Instances like this.
Quick question, slightly quick question. The particular example you gave where you've got a diamond and zero space. Does that still contribute to a growth, or did you make the best space back?
It depends on how we define it. So I think the important feature is that the thing is got a non-empty space left problem.
But even had say a closed universe, I think still this issue.
Right.
I mean, more general thoughts about infinitely ferromagnet type cases. I mean, it feels like the right thing to say for the actual ferromagnet situation is real ferromagnetism, infinity to be an approximation, and then I think in that situation, obviously, I think you could start appealing to pragmatic or more pragmatic conclusion. I mean, I guess that's a more interesting case would be where I've got reason to think that I genuinely got an infinite system. I mean, say take color symmetry breaking, you think you've got as one of the greater symmetry, we do kind of tend to think there's infinite. I mean, I'm trying to think, on one hand there it feels as if imposing kind of long-term convergence criteria on fluctuation effect, I mean, kind of feels unmotivated as if presumably if the universe really is infinite, then if you look at how 387 years from now, from here to somewhere where the direction of how some breaking has totally uninteresting probability or all tend to have 10 to the 387 of the equation. And on the other hand, worries about kind of globally defined observables don't seem quite so worried about, because the reason why I'm worried about, say, an overlapping randomization for a ferromagnet is actually the real system I'm approximating about. I can really do things with that property, whereas the direction of the colours that you make the jet out of it, it doesn't have a lot of practical consequences. I don't know especially good for it on how all this goes to know what to conclude from
So, and this is exactly why we were pursuing the line of interrogation yesterday about whether in the case of symmetry breaking in real quantum field theory, there's something that stands to the Higgs mechanism as polarization stands for ferromagnet. That's one way to, when people always say the ferromagnet's finite, coffee's finite. One way to preserve the kinds of lessons you might want to draw from the ferromagnet against this observation is to show that they apply as well to systems that are genuinely infinite. So I want to know whether there's things people regard as physical differences. But I have another, I mean, it's not a knockdown drag-out reply to my cup of coffee is finite, but Giant aggressively pursues the argument that the thermodynamic limits incompatible with atomism. We know there's finitely many atoms in your cup of coffee. As your cup of coffee steams, the account of the steaming, the phase transition offered by the thermodynamic limit says your cup of coffee is a volume within many subsystems, therefore it's a consistent with atoms. And who's an atomist? Trying to meet the objection on its own terms, one strategy is who says atomism a priori? We haven't got like the final theory of a cup of coffee yet, and it might not be atomistic. Lucretius might not have gotten it right, and it might be that whatever the final theory of a cup of coffee is, treating the cup of coffee as thermodynamic limit is going to have features that carry over into time. So to declare that the thermodynamics of idealization is to make a guess about the final theory of a cup of coffee. Guess that the final theory of the cup of coffee features the thermodynamic limit exhibits a virtue of invoking infinities of the present. And that's just a guess.
Just two more questions. I think we can take through.
Oh, if David has something extra to say, I think that.
Oh, well, it was pretty brief. I mean, my concern is just methodologically. I worry that if we start getting a situation where too much of physics is being postponed about bound theory. I mean, I can't kind of see the case for saying there's going on this theory of instantiate breaking in from field theory to I think we want to do whatever it is we should do that because it is associated to black hole operation. We the kind of consensus among physicists would really understand the physics topic well. It would be a bit worrying if that company is so exposed to mathematics. It kind of feels as if you don't know anything. There's some attractions. It's a schematic position, but it's
I didn't say it was convincing.
So I want to talk about the Halverson states that you're talking about, the converge to a
Yeah.
So are those the states that he talks about in his later studies paper that are in a sharp position and they're not building any momentum operator?
So the states, those states live in a non-cyclical Hilbert space.
Right.
So those states states on a representation of the file relations that isn't continuous. I believe those states, the states I'm talking about, states on an algebra generated by a representation of an which that's continuous. Abilities on algebra. This is the case for but I believe that the states I'm talking about restricted to the biological agree with the states that divide us in the non-cyclical.
Right, good. So, I mean, so there's a case to be made that they're just the versions of those states in the particular representations that you're talking about.
Yeah, so one trick to
Yeah. Yeah, I mean, what I wanted to point out then is, you know, if you look at those states in non-relativistic quantum mechanics, you think, well, there's very little physical motivation to think that we should have anything to do with these states because who cares about having a sharp position? You know, we're doing quantum theory and presumably we're not Bohmians or else we'd be doing Bohmian mechanics. And so, you know, why do we want states in a sharp position? But I was going to say, if you take that to a theory of something like electromagnetism, all of a sudden the configuration variable instead of being position is a gauge field, and then the momentum variable, or function momentum variable, is a constraint. And you want it to be the case that the constraint vanishes through all the gauge invariant states, and therefore, the gauge invariant states had better be eigenstates of the constraint. And so, you're going to get states that look a lot like those that are sort of sharply peaked states of the constraint. So they're going to be like the momentum versions of the ones that you're talking about in quantum mechanics.
Good, good.
Yeah. So that's sort of a friendly comment.
Right, right. But it's unfriendly to people who want to talk about exact position eigenstates and
Right.
ordinary quantum mechanics. I myself don't, but I defend. I don't think it's uninteresting. It's nice to have the representation of the capacity. At least so you can adjudicate whether we want to talk about it.
Just one last question.
There is, one of the things was, what is the alternative to optical stamps? So, we couldn't do this conditionalization, couldn't do. And there is an extension of classical probability by Renyi that was developed a while ago that would allow, even though you could have the algebra that you have to think finite, so that there's no measure. So you have you can think of the universe for the and you want to have that have measure one. Or you could have unions so you have these unions of things. They're giving you the universe. And that doesn't have to have still have the thing well defined and loosen up that thing. So you can have non-measurable, and he was looking at things like uniform measures on a sphere or something. You know, there are all these measurability things that come up, and it's a very natural extension of classical probability, where you're not using the Kolmogorov acids. You have a general thing, and you can define. You still have the relevant conditional probabilities appropriately defined, and it's very worked out. Very know what you want to see. So it shouldn't be just, oh, if I allow this, then I just have nothing. It should be, if it turned out for one of these problems that you could set it up in a Randy kind of system where you have the relevant things you want to conditionalize all inputs, then why not?
Yeah, so the despair about preparation, the despair about a particular strategy for applying preparation to deal with this conditionalization. There might be the way to restore hope about preparation.
Or at least there's one well
Yeah.
worked out.
Yeah.